Hi everyone. In this video, we will see the Park transformation, or it is also known as the DQ transformation, where DQ stands for the direct and the quadrature axis. As we know that the DQ transformation is very helpful to convert my two-phase, which is placed orthogonally, into the DC values. And further, if we have the DC values, or in other words, we can say that if we have the decoupled values in terms of the torque and the flux, which is happening simultaneously uh, in my AC machines. So once I get the decoupling, that means if I can have the control on torque and the flux independently, just my DC separately except DC motor. So it is very simple to control those values by using the PI controller. So therefore, the Clark's transformation and the Park's transformation both serve this purpose uh, to convert my three-phase ABC reference frame, which is happening in my AC motor, first into the two phases orthogonal reference frame. And these two reference frames, one is the ABC and after the two phases reference frame obtained from the Clark's transformation, both are the stationary reference frame, and subsequent to it the last transformation is being done by using the Park's transformation, and this Park's transformation converts that two phases into the something like a DC values, the direct axis and the quadrature axis. However, this frame is the rotating frame. So first initial two frames are the stationary frame and the third is the rotating frame. So this helps to control my AC motors very easily, and torque and the flux can be controlled independently. So let's begin. So here I have taken one rotating example of the three phase ABC reference frame is being shown over here, which is the actual reference frame is being simultaneously is being happening in the my AC motors. And here the red, blue and the green are the three phases, and where the sky blue is showing the arbitrary vector which is rotating. This frame is the stationary frame. However, the amplitude is changing continuously and the phase is also changing. So therefore, this is the phase changing 120 degree apart. All the three phases are is being converted into the two-phase reference frame by the Clark's transformation. And the Clark's transformation, here it is being shown over here. So Clark's transformation, what it does, and which we have seen in the previous video also, that it converts my three-phase ABC reference frame into the two phases, which is placed orthogonally. So the same reference frame which we have seen just now is being converted into my here the two phases reference frame, which is the alpha and beta. So blue line shows the alpha frame and the red line shows the beta frame, and their amplitude is changing continuously, and the sky blue line is the arbitrary vector which is rotating. Again here, this can be seen easily that this reference frame is also a stationary reference frame. I mean, alpha and beta is not rotating with respect to my arbitrary vector, which is shown in my sky blue line. So my arbitrary vector is rotating with some arbitrary, let's say, speed or the velocity, but my alpha beta reference frame is the stationary reference frame. So up to here we have seen that how it is being converted from the ABC to the alpha beta. To convert this further into the DC values here, uh, just let me show you that this reference frame, this phase, which is my alpha, and this is my beta. So they are the alternating values, but instead of three phases, there are only two phases now, and the both phases are 90 degree apart from each other. So to convert further this into my stationary, this frame which is stationary into something like DC. So instead of this value, if I can have this some stationary value over here, something like that with respect to my reference line, if I can have the DC value something like this, So which is easy to control by my PI controller. So this is being done with the help of my Parkes transformation, also known as the DQ transformation. So the two phases is being converted. It has mean that alpha beta reference frame is now being converted into DQ frame. But here here I can see that the D and Q, they both are also rotating with the arbitrary vector. Here the blue line is shown here. This is nothing but the D axis, and the red is my Q axis, where again the sky blue line, which is shown over here, is my arbitrary vector. So along with this, along with the arbitrary vector, now my Q and D both are rotating. So if I'll just see, if someone is standing at this arbitrary vector, and if that person will see that what is the uh, D distance and what is the Q distance from this arbitrary vector, as they both all three are rotating on the same speed, so therefore it looks like that everything is constant. So from here, by looking from this arbitrary vector, if I'll just check the D or Q, it seems like that both are constantly varying with the time. I mean, they are not varying, they are constant with respect to the time. So therefore, this thing is being converted from the three phases to two phases, and now the DC value. So this is being done by the Parkes transformation. So now we will see that how it is being converted, and we will see the derivation of it. So now we can see the derivation by which we can perform the DQ transformation. So to have the derivation, let me make one phasor diagram over here. So let's have that we already seen that alpha and beta, they are the stationary frame. So I'm just drawing the alpha beta over here. So let's say this is my alpha and beta over here. All right, and let's say that my D and Q, again they both are orthogonally placed, or they are 90-degree apart. Let's say that my D frame is rotating with some arbitrary speed, and it has the position with respect to alpha. Let's say it is having an angle of theta, which gives me the angular position of my DQ frame, and the Q will be 90 degree, having 90 degree apart from my D axis. So this is my Q. So let's say I'm taking one function, or let's say the value f. F can be anything. It can be current, it can be voltage. Uh, so this, let's say I'm having the unit vector ft over here. Similarly, I have a unit vector fq over here, and a blue vector which we have seen in the previous images also, that it is an arbitrary vector which is rotating in space. So let's say I have one arbitrary vector over here. So let's say this is, I'm denoting one vector which is rotating uh, with the same speed as my D and Q reference are rotating. So from here, let's find out the value of Ft and Fq in terms of the alpha beta. So here, first this vector will have the projection over my alpha axis, similarly over my beta axis. So the projection of this vector will give me this f of alpha and this f of beta. Similarly, the projection of this vector on the unit vector of fd cap, and similarly the projection of this vector on my unit vector of FQ will give me this is nothing but FD and this is nothing but FQ. So now I can have this relation over here that FD cap is equals to, if I'll just take this unit vector over here, FD cap here, having the projection over the alpha, I can say that this is in terms of the theta itself, right? So cos theta and f of alpha cap, and plus having the projection over the beta axis, so this will give me the sine theta and f of beta cap. Similarly, having this unit vector fq is equals to, so having this unit vector projection over here, so I'll get in term on the alpha axis, so I will have the sine theta f of alpha and plus cos theta, and this is f of beta cap over here. And this arbitrary vector f alpha beta is equals to alpha projection on the alpha axis. So this is the projection over the alpha axis with the cap over here, and plus f of beta dot f of beta cap. So the projection of the arbitrary vector on each of the two new unit vectors implies the dot product. So taking that into account, I can say that the FD is equals to FD cap dot F alpha beta vector of it, which is equals to, putting the FD cap value from here, I'll get the FD is equals to, this is equals to cos of theta, and this will become f of alpha, and plus sine of theta, and this becomes f of beta. Similarly, the FQ is equals to the FQ cap and the same arbitrary vector, and this will give me that minus of sine theta, and this is f of alpha, and plus cos theta, and this is f of beta. So putting into the matrix form, now I can have the two quadrature and direct axis value in terms of my alpha beta, and this is cos theta, sine theta, and minus of sine theta and cos theta into f of alpha and f of beta. So here this matrix is known as this matrix, which is presented by this, is known as my Parkes transformation matrix. So to have the FOC control, first we need to get the feedback from my motor, whether it is a current or the voltage. So let's say I'm taking the current control. So I will take the three-phase current feedback from my motor, and I'll perform the Clark's transformation, which will convert into the alpha beta reference frame. And then in the forward mode, I will perform the Parkes transformation, which will convert into the TQ rotating frame. Once I will have the D and Q values, now I can give this DQ values to my PI controller, which will act based on the taken feedback from my motor, and again subsequently will generate my control signal. So this control signal again going before giving back to my motor, we need to perform the reverse transformation. So first we need to perform the reverse Parkes transformation, which will convert this DQ value again into the alpha beta frame, and again performing the reverse Clark's transformation or the inverse Clark's transformation, which will convert alpha beta values into the three-phase ABC values. So all these values again now we can give it back to my motor by using the PWM inverter. So in the next lecture we will see that how these simulations being done through a block diagram technique. So I hope now we have understood that how the Clark's and the Parkes transformation is been done, and how they are helpful to convert the three-phase values into the DC values, and which is being or which is easy to control. Thank you.